So when we are testing proportions, proportions are estimated from categorical variables. And there are usually two possible outcomes. This is a simplistic way. It can be yes or no. Sometimes it doesn't come like as simple as yes or no. Sometimes the data doesn't have yes or no, but it has actual values, and you yourself turn the data into a yes, no. For example, you may say anybody with a value above this cutoff, you determine a cutoff. Above this value is positive. Below that value and below is negative. And then you create your binary outcome. So sometimes the data are not in actual binary form, but you can create it in binary. Sometimes they are in binary. Assume this is HIV, an HIV test. It will either be positive or negative. Assume this is a gender. It will be male or female. Assume this is death. So one will be alive or dead. So some of the variables come directly, where you only directly in the categorical form, where you need to create two proportions. There are also data that doesn't have only two proportions or two outcomes, yes, no. And it has, they are still categorical, but the categories are more than two, okay? And so that is a different level where you may have yes, no, indeterminate. Okay? The value could not determine. And so data comes in different flavors, but in this case, we are only going to consider the binary outcome. So first, we have to calculate a proportion, which is usually positive outcome over n, and it gives us the proportion denoted here as a p bar. And when it both, and 1 minus p gives you the q. And so when the n, the sample size times p, and n times 1 minus p, if each of them is at least 5, then these proportions do approximate a normal distribution with the mean and the standard deviation as given here. Remember that the standard deviation in a continuous variable is sigma, but the standard deviation of a proportion is p q over n, where q is n minus 1, and you take the square root. The variance of a continuous variable is sigma squared. The variance of a categorical variable is just pq over n. So when you take the square root of the variance, you get the standard deviation. Okay, so this is again showing what we had said, that the two groups you compare, n1 times p1 should be at least equal to 5, n1 times q1 equal to 5 at least, greater if it's better, and so is n2. So then the proportions will be approximating a normal distribution. And so we set our null hypothesis that proportion 1 minus proportion 2 is equal to 0. In other words, proportion 1 is equal to proportion 2. And the alternative, that P1 minus P2 is not equal to 0, meaning that P1 is not equal to P2. And once again, not equal means it is a two-sided test. And we can calculate our Z observed by getting the parameter under the test under the null hypothesis, P1 minus P2 minus the hypothesized value of 0, and then you divide it by the variance of the difference. And in this case, it is P bar Q bar over N1 plus P bar Q bar over N2, and then you take the square root. How do we get P bar? We get the P1 plus P2 divided by 2. Then we get the average of both proportions, which is the P bar. We can also get P bar by doing x1 outcomes in group 1 plus outcomes in group 2 divided by the sample size of group 1 plus the sample size of group 2. Then we get P bar. Okay. And of course, we say that this is a two-sided test, and this is how we calculate the confidence interval. We get our test statistic, which is P1 minus P2, plus or minus the standard error of the mean. Standard error of the mean times you remember the standard error of the mean is equal to sigma over root n. And we get sigma over root n for continuous variables, multiply it by the z value. For categorical variables, this is what represents the standard error of the mean. We multiply it by the z, and then we get the steps we are going to go below and above the test statistic, like we did the other time. The only difference now is that we are using proportions. Okay, so let's see an example. Maybe it becomes better when we see an example. In a study of the homeless, two samples provided the following data. Males were 150, females were 200. Those who were underweight X are 21 in this group in the males, 48 in the females. The proportion here is this divided by this gives you 0.41. 48 divided by 200, 0.24. I beg your pardon. 21 divided by 150, 0.14. 48 divided by 200, 0.24. So question, can we conclude from this data that there is a difference in proportions of underweight between the two populations? Or we can ask this question differently. Can we conclude that among the homeless people in this study, underweight differs by gender? That is still the same question, as you can see on the slide. So now we go through the manipulations. So as you can see on the slide, if we go back to the slide, we now have our alpha of 0.05, our default. We have our hypothesis, P1 minus P2 is equal to 0. Our null, our alternative, is not equal to 0, indicating it's a two-sided test. Then we have our test statistic, P1 minus P2, minus the hypothesis value under the null, which is 0, divided by the standard error, which is P bar cube over N1, P bar cube over N2. And remember how we get P bar, which is P1 plus P2 divided by 2, or X1 plus X2 over N1 plus N2. And once we do all this manipulation, we actually end up with the minus 2.31. And I now want to turn to the board to see how we deal with that value of the observed Z. Okay, so recall from our normal distribution diagram. We have an alpha of 0.05, but we are using a two-sided. The null hypothesis is P1 is equal to P2, which is the same thing as P1 minus P2 is equal to 0. The alternative hypothesis is that P1 is not equal to P2, which is the same thing as P1 minus P2 is not equal to 0. So because we are using a two-sided test, our alpha is divided into 2. So here we have 0.025, which is alpha over 2. And this side we also have 0.025. Now when you go to the Z tables and look for an alpha of 0.5, the value, the cutoff value is 1.96, and because of symmetry, it is minus 1.96 this side, and here is our 0. Now, where would minus 2.31 lie? Remember, this minus 1.96 and positive 1.96 are referred to as the critical values. You recall that from the previous session. This is the critical value, and this one also is a critical value. Now, to the extremes of the critical value in black is what we call our rejection area. So this is a rejection area. This is where we reject the null hypothesis, but this one also is a rejection area. And anything in between the two is a non-rejection area. Okay, since we have our 0 here, minus 1.96 is here, where do we expect minus 2.31 to be? This side or this side? Remember, as we move towards 0, we are becoming more positive. As we move away from 0, we are becoming more negative. So our value, this one, the Z, from the observed data that we calculated in the previous slide, will lie somewhere here because it is more negative than 1.96. And as you can clearly see, our observed value lies in the rejection area. So given that it is less than 1.96, remember it is more negative, so it is less. So once we place our value here, it falls in the rejection area on the negative, on the lower side of the table. If this value had been, if this observed value had been the Z observed, if it was 2.31, the positive one, again, it would have been here, this time on the upper side, and again, this would be in the rejection area. So this means that we reject the null hypothesis. The data shows us that we reject the null hypothesis and conclude that a proportion in one group is not equal to proportion in another group. So we now have evidence to show that the two proportions are statistically different. Okay. Now we can calculate the confidence intervals using this formula, and here we've shown you how to do it by hand. But of course, you can always, the computer will always spit up this information for you, spit it out for you. But then, how can we use this confidence interval? The confidence interval ranges from minus 198 to minus 0.02. Remember, this is less negative than this one. So, what does this mean? We have two interpretations of the confidence interval that we saw earlier on. One is that if we repeat this study and sample from the same reference population using the same sampling technique and getting samples of the same size, 95% of those samples, the difference in proportion will lie between minus 1.80 and minus 0.02. That is one. But the second is that based on this sample alone, we are 95% confident that the true difference in the population parameters is between 0.18 and 0.02. And we saw that. But now I want to take you to another level. We can also reject the null hypothesis using the confidence interval. So far, if we go back to this board, we have seen that we can reject the null hypothesis based on the observed Z value or the observed T, the T that we calculate from the data. And once that value falls in the rejection area, then we reject the null hypothesis. Now, we are moving to another way of rejecting the null hypothesis, where we use the confidence interval. So, under the confidence interval, we had this null hypothesis that P1 minus P2 is equal to 0. And we had the alternative that P1 minus P2 is not equal to 0. Please note that when we are using the confidence interval, to reject the null hypothesis, it is all based on this value that is hypothesized under the null hypothesis. It all depends, rejection or failure to reject the null hypothesis using the confidence interval depends on two things. One, the value that is hypothesized under the null hypothesis, and two, the confidence interval itself. In the previous example, the confidence interval was minus 0.18 to minus 0.02. So how do we use the confidence interval and the value under the null hypothesis to reject the null hypothesis? If, and this is a big if, so let me make it really big. If the value under the null hypothesis is not, and I'm making this one also big, is not included in the confidence interval. So if the value under the null hypothesis is not included in the confidence interval, then we reject the null hypothesis. Then we reject the null hypothesis. Okay, let's see this example here. This is the value under the null is 0. P1 minus P2 is equal to 0. This is the confidence interval. Is 0 included in this confidence interval? No, because it ranges from minus 1.8 to minus 0.02. 0 is still on this what? Side. You can see that 0 is on this side, is still greater than this one. 0 is this side. So this confidence interval from here to here does not include what? 0. And since it doesn't include 0, the value under the null hypothesis is not included here, then we can use this to reject the null hypothesis. So far we've seen two ways in which we can reject the null hypothesis. How can we reject the null hypothesis? We have so far seen two ways. One is using the Z observed or the T observed. And that one we saw when we press it in the normal distribution curve. Two is we use the confidence interval. And we use, how do we use the confidence interval? If the value under the null is not included in the confidence interval, then we reject the null hypothesis. If the value is included, then we fail to reject. And now let me give you another example. Okay, now assuming that, this is just an assumption, assuming that we had got these values, minus 1.81 to 1.28, assuming this was our confidence interval, would we have rejected the null? Look, if you come from minus 1.8 to positive, it means you have crossed the what? The 0. In this case, it would mean that the 0 is a part of is included in the confidence interval. So in this case, what happens? We would fail to reject the null. We would fail to reject the null. Why? Because this value is included in the confidence interval, the value under the null. And many people make a mistake because in class we use the examples of 0 when we are teaching. Many people just cram it that it is 0. It is not 0 per se. It is the value under the null. The value under the null hypothesis. Is it included in the confidence interval or not? Okay, so we will keep these two ways of rejecting the null hypothesis, and then we come to the third. There are three ways, but so far we've covered two, and then we shall come to the third. Okay, now again back to Stata. You can do that analysis like we had the SD test and the T-test. You can actually, in this case, you use the proportion test, which is a PR test. So you can use a PR and put the variable name. If your data are in memory, then you put the what? You put the proportion you are going to assume. This is a one-way test, one proportion. If it is 2, then you're going to do PR test, variable 1 is equal to variable 2, and then the rest will come by itself. Okay, so let's see an example using Stata. In a study, we've gone back to the homeless. Remember our homeless example, we are still at it. So now we do PR test N in group 1, 150, proportion 1, 0.14. N in group 2, 200, proportion 0.24. And then look at the null hypothesis. Difference is proportion x minus proportion y is equal to 0. In the middle here is the alternative hypothesis of difference is not equal to 0. Look at the p-value. P-value is 0.02. It is less than alpha of 0.05. And if the p-value is less than alpha, then we also reject the null hypothesis. So the third way in which we reject the null hypothesis is by using the p-value. And we reject if the p-value is less than alpha. Then we do what? We reject. If the p-value is equal or greater than alpha, then we do what? We fail to reject. Remember this terminology. We either reject or fail to reject. So there are three ways in which we can reject the null hypothesis. 1, we can use the p-value. 2, we can use the confidence interval. 3, we can use the observed Z or T statistic. Now, these three will always agree if your data set is in good order. Because the first thing that the software does is to calculate this. Then it uses this to calculate this. Then it uses this also to calculate the p-value. So there is no way you're going to see this one is saying you reject, but this one is saying fail to reject, and this one is saying reject. When you see the three not agreeing, then it means that there is a problem with your data. There is a problem with your data. And if we go back to our static example, we can now see from here, using the p-value, that the p-value is less than 0.05, the default alpha. Therefore, what do? We reject the null hypothesis. But you can also look here at the confidence interval. This is the difference, and this is the confidence intervals of the difference. It ranges from minus 0.181 to minus 0.0185. Is 0 included here? No. 0 is this side, which is the value under the null. Therefore, we reject the what? The null hypothesis. But also look at the Z value. Is minus 2.33. It is less than minus 1.96. So it follows in the rejection area. So whether we use the Z or the confidence interval or the p-value, the three agree. Okay. So we have other examples for you, and you should be able to look at these examples in the data, and then be able to make conclusions. So this ends our session of hypothesis testing, inferential statistics using checking means, two group mean or one group mean, two group one proportion or two proportions. As part of this distance education learning for this module, we provide you with a data set of the low birth weight study. And we have a practice assignment for you on the last slide. You have to go to this data set and do the following. You convert birth weight in kilograms, this way, because it is in grams. And then you check whether birth weight differs by smoking status of the mother. And remember, you do an SD test, then you do a T test. And then we also have one for proportion for you, where we use the proportion of those who are low birth weight using the variable low, and we want you to check whether they differ by race and all these other variables. Going through, you can always go back to those examples, and then you will come up with your conclusions. So next time, we're going to do hypothesis testing for special cases, which is not part of this talk. The special cases is a different talk, and that will be another session. What were our learning objectives? If we go back to the beginning of the slides, and we look at what was it that we wanted to achieve at the end of this talk of financial statistics. Our learning objectives were that at the end of this talk, a student should be able to distinguish between a type 1 and a type 2 error. And you recall, we went through that very well. Type 1 error, probability of rejecting the null hypothesis when it is true. Type 2, probability of rejecting the null, or failing to reject the null hypothesis when it is false. Our second learning objective was that you should be able to formulate a null and alternative hypothesis and test for differences between means and proportions. We've done that. We've seen the decision rule, we've seen the critical values, and we've seen the p-values. We've even gone beyond our learning objectives, and so that there are 3 ways in which we can reject the null hypothesis. We can use the observed, the value of the observed Z or T. We can use the confidence intervals. We can use the p-value. Thank you very much. Have fun.